So I think I am audible. Am I audible?
Yes, sir.
Is the screen visible?
Yes, sir.
Yes, sir.
So yesterday in Heisenberg picture and Dirac bracket notation, we have discussed some important concepts, and I think let us have a detailed discussion in Schrodinger formalism of a differential equation. So yesterday we were discussing your expansion coefficient. So in Schrodinger formalism also, the expansion coefficient is being discussed in detail by Erwin Schrodinger. So it is shown in the screen. So you see expansion of an arbitrary wave function as a linear combination of energy eigenfunctions. So you know when E cap, the energy operator, is operated over a wave function psi, you will have your energy eigenvalue E. So if there are a number of energy eigenvalues as a result of the measurement of energy of a microscopic matter, then let E1, E2, E3, so on and so forth, En be the possible energy eigenvalues of the system corresponding to the eigenfunction psi1, psi2, psi3, so on and so forth, psi n respectively, where psi is a function of the position vector r. So all the quantum mechanical operators corresponding to the observable quantities are Hermitian because the eigenvalues of the Hermitian operator are always real, which I was discussing yesterday in your Heisenberg formalism. Therefore, the operator corresponding to the energy, that is the Hamiltonian operator, is also a Hermitian operator. The Hermitian property of the Hamiltonian operator H cap yields the following properties for the energy eigenvalues and eigenfunctions. So first is the energy eigenvalues En are always real. The energy eigenfunctions psi n form a complete orthonormal set, that is they are normalized as well as orthogonal, and these eigenfunctions define the so-called Hilbert space named after the famous mathematician David Hilbert, and I was discussed it in detail yesterday while I was discussing your Dirac formalism or Dirac bracket formalism. So any arbitrary wave function that is continuous, single valued, finite, and describes a possible quantum state can be expressed as a linear combination of eigenfunctions psi n, which is a function of the position vector r of the Hamiltonian operator H cap, and we can write psi is equal to summation n Cn psi n, where psi n is a function of position vector r. And the expansion coefficient Cn can be real or complex number. So Cn is used to expand the wave function psi into a number of wave functions. So how can you evaluate Cn or the expansion coefficient? In order to evaluate the expansion coefficients, we have to multiply both sides of the equation by the complex conjugate of one of the psi n's, say psi m, and integrate over Q's region of hermiticity. So your integration psi m star psi dqr is equal to integration psi m star summation n cn psi n dqr. So your summation n cn integration psi m star psi n dqr is equal to summation n cn del mn is equal to cn. So it follows that Cn is equal to integration psi n star psi dqr. So what is the physical significance of expansion coefficient Cn? So if psi is a normalized wave function, then you can write integration psi star psi dqr is equal to 1, which is nothing but summation m cm psi n star multiplied by summation n cn psi n dqr. So now you have your summation m comma n cm star cn integration psi m star psi n dqr is equal to summation m comma n cm star cn del mn, which is equal to summation n cn star cn. So you can write summation n modulus of cn square is equal to 1. Next, we have to consider the expectation value of q in the state psi. So your average value or expectation value of q is equal to integration psi star q cap psi dqr, which is equal to integration summation m cm psi m star q cap summation n cn psi n dqr, which is nothing but summation m comma n cm star cn qn integration psi m star psi n dqr, which is equal to summation m comma n cm star cn qn del mn. So the expectation value of q is equal to summation n cn modulo square qn. By exactly the same argument, we see more generally that expectation value of fq is equal to summation n modulus of cn square f of qn. We thus conclude that a modulus of cn square is the probability that in the state psi, the observable represented by the operator q cap has the numerical value qn. In other words, Cn square is the probability of finding the value Qn when Q is measured. So the coefficient Cn is sometimes called the probability amplitude. So in physically, if you consider physics point of view, then the expansion coefficient is called probability amplitude, and it gives the probability of finding the value Qn when capital Q is measured. Then completeness relation, which I was discussing in the previous class while explaining you the Dirac formalism. Every physical quantity can be represented by a Hermitian operator, which has a complete set of orthogonal eigenfunctions psi n, such that your n is equal to 1, 2, 3, 4, so on and so forth. And every physical state psi can be expressed as a sum of summation n cn psi n, where your cn is equal to integration psi n star psi dqr. The relation integration integration modulus of psi square dqr is equal to summation n modulus of cn square is equal to 1 is called the completeness relation or Parseval's formula. So Q is called an observable if it is represented by a Hermitian operator Q cap and possesses a complete set of eigenfunctions. So this is the completeness relation where your integration modulus integration size modulus psi square dqr is equal to your 1. Am I audible?
Yes, sir.
Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Then energy of an arbitrary quantum state. If the system is in any arbitrary quantum state psi, which is a function of r expressed by the equation I have shown you in the screen, then the probability of finding the system in the nth state is given by Cn square. So if we measure the energy of the system the possible values E1, E2, E3, so on and so forth, En with the probabilities C1 square, modulus of C2 square, modulus of C3 square, so on and so forth, modulus of Cn square respectively. Therefore, the energy of the system in an arbitrary quantum state psi will be expressed as E is equal to C1 square E1, C2 plus C2 square E2 plus C3 square E3 plus so on and so forth, En square En. Then let us discuss the closure relation. So psi is equal to summation n Cn psi n, and your Cn is equal to integration psi star n psi dqr. So your psi is equal to summation n integration psi n star, which is a function of r dash vector, psi which is a function of r dash vector, dqr dash psi n which is a function of r. So if you interchange summation and integration, you have your psi which is a function of r is equal to summation n psi n star psi n psi dq r dash, where the psi n is a function of r and psi is the function of r dash. And psi n star is a function of r dash. So psi r can also be written in the form psi is equal to integration delta r minus r dash psi of r dash dq r dash. So now compare these two relations and you have your summation n psi n star r dash vector psi n of r is equal to your delta r minus r dash, and this is the closure relation. Am I audible?
Yes, sir.
Yes, sir.
So let us discuss the general solution of the time-dependent Schrodinger equation in terms of linear combination of stationary states. So you know that in stationary states, the states are independent of time. And let E1, E2, and E3, E1, E2, E3, so on and so forth, En be the possible energy eigenvalues of the system corresponding to the eigenfunctions psi1, psi2, psi3, so on and so forth, psi n respectively. So nth stationary state can be expressed as psi n is equal to psi n e to the power minus I En t by h cross. So you know the principle of superposition of quantum states. So if you use the principle of superposition of quantum states, and if psi1, psi2, psi3, so on and so forth, psi n are different possible solution of the Schrodinger equation, then the linear combination of this solution is also a solution of the Schrodinger equation. So this linear combination can be expressed as psi is equal to C1 psi1 plus C2 psi2 plus so on and so forth, Cn psi n. So your psi is equal to summation n Cn psi n, where Cn are the expansion coefficient and which can be real or complex number. Thus, this equation expresses a general solution of the time-dependent Schrodinger equation in terms of linear combination of stationary states. Okay, am I audible?
Yes, sir.
Are you getting it?
Yes, sir.
Then let us discuss velocity of Debye wave. So in the first class and the subsequent class, we have discussed how Debye expression, that is lambda is equal to h by p, express the matter waves. So matter wave has two peculiar behaviors. it is wave as well as particle. So its wave behavior is expressed by lambda, and its particle behavior is expressed by p, and lambda is equal to h by p, where h is Planck's constant. So the velocity of de Broglie wave is nothing but velocity of matter waves or velocity of microscopic particle in an atom or in a nucleus or in a quantum mechanical state. So the velocity of de Broglie wave associated with a particle can be described in the following manner. According to de Broglie hypothesis, a free material particle having an energy capital E and momentum p is equal to h cross k can be represented by a wave. So let us choose a plane wave psi, which can be expressed as a to the power I k dot r minus omega t, where k is propagation vector, r is your position vector, omega is angular frequency, which is equal to 2 pi nu, a is equal to amplitude of the wave, and nu is the frequency. And your magnitude of propagation vector k is equal to 2 pi by lambda, where lambda is the wavelength associated with the particle or matter wave. So your 2 pi by k is equal to 2 pi h cross by h cross k is equal to h by p. So your psi depends upon the phase k dot r minus omega t and is represented by alpha. So the phase velocity u vector of the wave is equal to the velocity with which a point of constant phase travels. The velocity of constant phase travels. The point which is having a constant phase, the velocity of that point is called the phase velocity. So alpha is equal to k dot r minus omega t, and it is a constant. So now by differentiating it with respect to t, you can have k vector dot dr by dt minus omega is equal to 0, because omega is constant. So your k dot u, because u is equal to dr by dt, and the phase, it is phase velocity, minus omega is equal to 0. K dot u minus omega is equal to 0. So the propagation vector k and the phase velocity u are in the same direction. So k dot u is equal to k, because cos theta is equal to 1 as theta is equal to 0, because they are being in the same direction. So your u is equal to omega by k. This represents the magnitude of the phase velocity or the wave velocity. So you can write u is equal to h cross omega by h cross k, where e is equal to h nu or h cross omega, and p is equal to h cross k. So u is equal to e by p, where e is equal to energy and p is equal to momentum. So phase velocity can be calculated from the ratio of energy of the matter wave and momentum of the matter wave. But when you have a photon, so photon is having mass 0 and velocity 3 lakh kilometer, 3 into 10 to the power 8 meter per second, or 3 lakh kilometer per second. So for photon, your E is equal to P multiplied by C. So your C is equal to E by P. So your U is equal to C. So velocity, phase velocity of photon is velocity of light. Are you getting it?
Yes, sir.
Okay. So for
Yes, sir.
photons, for photons, you see your phase velocity is velocity of a light. So photon is a light. Phase velocity of a particle, that is non-relativistic matter. So the kinetic energy of a particle, like that of electron of mass m moving at a non-relativistic speed v, is equal to half mv square, is equal to p square by twice m. So the phase velocity of de Broglie wave associated with electron-like particle is equal to E by P is equal to P by twice m is equal to P is equal to mv by twice m is equal to v by 2. This shows that phase velocity of the matter wave associated with a non-electric particle is equal to half of the velocity of the particle. So if the velocity of electron is equal to 2 into 10 to the power 5 meter per second, then its phase velocity will be 4 into 10 to the power 5 meter per second. So the phase velocity of electron-like particle or neutron-like particle or proton-like particle at a velocity smaller than that of velocity of light, very, very smaller than that of the velocity of light, the phase velocity is twice that of the velocity of the particle or wave packet. And for relativistic motion or the particle at rest, mass m0 moving with velocity v, which is comparable with that of light, that is v is very, very nearly equal to c, your E can be expressed as m0 c square by 1 minus v square by c square to the power half, and P can be represented as m0 v divided by 1 minus v square by c square to the power half. So your velocity, phase velocity, which is expressed in terms of E by P, can be written as c square by v. Because if you divide the E by P as shown in the screen, you will have c square by v. So c square by is very, very greater than 1. Or c square by v is equal to c by v is equal to greater than 1, and multiplied by c is greater than c. So c square by v is equal to c multiplied by c by v. So c by v is greater than 1. So c multiplied by is a number which is greater than 1 is greater than c. So the phase velocity of Debye wave associated with the relativistic particle is greater than that of the velocity of light, which is impossible according to Einstein's relativistic formalism. So the velocity of material particle is always less than the velocity of light according to relativistic theory. So the phase velocity of matter wave is greater than the velocity of light in vacuum is impossible. So this is an apparent contradiction with the special theory of relativity. So your velocity of particle both for relativistic and non-relativistic motion is different from the phase velocity of Debye wave associated with it. This puzzling disagreement is sometimes referred as velocity paradox of matter waves. Okay, so are you getting what is velocity paradox of matter waves? Or is it difficult, and I shall explain it again? You can see for relativistic particle, your velocity of or the phase velocity is greater than that of the velocity of light, which is impossible. Okay, and again you have different values for relativistic and non-relativistic one. So this is velocity paradox. Okay, can you have
Yes,
any velocity greater than velocity of light?
No.
No. So here mathematically it comes as the greater than velocity of light. So it is impossible, and it is called velocity paradox. Then dependence of phase velocity on wavelength. The total energy E of a particle of rest mass m0 and momentum p can be written as E is equal to p square c square plus m0 square c to the power 4 to the power half. So U is equal to E by P, which is equal to c multiplied by 1 plus m0 square c square by p square to the power half. So U can be written as c multiplied by 1 plus m0 square c square lambda square by h square to the power half, as shown in the screen. So for particle of zero rest mass like that of photon, your m0 is equal to 0. So U is equal to c. m0 is equal to 0, so m0 square c square lambda square is equal to 0, and 0 divided by h square is equal to 0. So your U is equal to c multiplied by 1 plus 0. So c multiplied by 1 is equal to c. So for particle of zero rest mass like that of photon, your U is equal to c, and U is independent of lambda. U is independent of lambda or wavelength of the matter wave. For material particle of non-zero rest mass, the velocity is always greater than the velocity of light in vacuum and depends on lambda. And the phase velocity of the matter wave, unlike light wave, depends upon the wavelength even in vacuum. So the vacuum behaves as a dispersive medium for matter waves. For photon, vacuum has no effect upon its motion. But for matter waves, it is behaves like a dispersive medium. For electrons, for neutrons, for protons, vacuum behaves like a dispersive medium. So in our attempt to represent particle by plane waves of type given by the equation I have discussed now, we have encountered the velocity paradox. The resulting phase velocity does not agree with the particle velocity. In fact, a particle is a localized object, whereas plane wave is an infinitely extended entity having no distinguishing marks to represent the localization of particle. Localization can be achieved by modulating the wave to form a wave group or wave packet. The wave packet or the entire group of wave travels with a velocity called group velocity and represented by v subscript g, which would correspond to the particle velocity. The individual waves which comprises the wave packet would travel with the wave phase velocity u. So before discussing your wave packet, let us discuss superposition of two waves. And from there, you can have an idea of groove velocity and phase velocity. The construction of wave packet needs the superposition of many waves. Here we attempt to construct the simplest case, or construct a wave packet by adding two waves only with wave function psi1 and psi2, which are functions of x, t, having the same amplitude and slightly different frequencies. So your psi1 can be represented as a sine omega t minus kx, and psi2 can be represented as a sine omega dash t minus k dash x, where k is equal to 2 pi by lambda and k dash is equal to 2 pi by lambda dash are the magnitudes of propagation vectors k and k dash respectively. So omega is equal to 2 pi nu and omega dash is equal to 2 pi nu dash are the angular frequencies. So by the principle of superposition, these two waves can be added to give a resultant wave whose wave function is psi. So your psi is equal to psi1 plus psi2. So you can write it as a sine omega t minus kx plus sine omega dash t minus k dash x. So this is 2a sine omega t minus kx plus omega dash t minus k dash x by 2 multiplied by cosine of omega dash t minus k dash x minus omega t minus kx by 2. So you can write omega dash is equal to omega plus del omega and k dash is equal to k plus del k, and your 2 omega plus del omega is nearly equal to 2 omega and 2k plus del k is nearly equal to 2k. So you can write psi is equal to 2a cosine of del omega t by 2 plus del x plus del kx by 2 multiplied by sine omega t minus kx. So your psi is equal to ak sine omega t minus kx. So you see your ak is equal to 2a cosine of del omega t by 2 minus del k by del kx by 2, and it is the resultant amplitude. So you see the resultant amplitude is t is not constant, and it represents a sine wave of angular frequency omega and wave number that are superimposed upon it, and it is a modulation of angular frequency half del omega and the wave number half del k. And the effect of modulation is to produce successive wave groups with graphs with gaps in between. So you can see in the screen, your first wave is a sinusoidal wave. The second wave psi2 is a sinusoidal wave, but the resultant wave is a modulated wave. It is neither sinusoidal, it is not a sinusoidal wave, and the amplitude varies with time. And it depends upon half del omega and half del k. And the phase velocity u is given by u is equal to omega by k. And the groove velocity is represented by limit del k tends to 0, del omega by del k is equal to d omega by dk is equal to dh cross omega by dh cross k is equal to d by dp. Okay, so initially we are having the particle velocity e by p. Here the groove velocity is d by dp. And the groove velocity of photon, you can see d by dp, and it is c because e is equal to pc. So if you integrate pc with respect to p, then your c is a constant, it comes outside, and dp by dp is equal to 1, c multiplied by 1 is equal to c. That is the groove velocity of photon is equal to the velocity of light in vacuum. Similarly, groove velocity of material particles. So you know E is equal to c square p square plus m0 square c to the power 4 to the power half. So your d by dp, if you differentiate this c square p square plus m0 square c to the power 4 to the power half, you have you can use the chain rule, and the solution will be b c square mv by mc square is equal to b. And for non-relativistic particle, your Vg is equal to v. It shows that the Debye wave group associated with a moving particle travels with the same velocity as that of particle. Particle moves with a velocity similar, exactly same as that of the groove velocity of those particles or those wave packets. Then a relation between phase velocity and groove velocity. You have your Vg is equal to d omega by dk, and your this can be written as d nu by d 1 by lambda. So your Vg is equal to u plus 1 by lambda du by d1 by lambda is equal to u plus 1 by lambda du by d lambda whole divided by d of 1 by lambda by d lambda. So your Vg is equal to u minus lambda du by d lambda. So this shows the relationship between the phase velocity u and the group velocity Vg. So if the waves are not in a dispersive medium, then u is a constant for all wavelengths. So your du by d lambda is equal to 0. And then your Vg reduces to u. This means that in a non-dispersive medium, phase velocity is equal to group velocity. In a dispersing medium, phase velocity is different from that of group velocity. So we have observed that superposition of two waves results in a chain of wave packets. The localization of particles is not possible with such a chain of wave packets. But this process of superposition gives an idea that a particle can be represented by a single wave packet which can be constructed by superposing a large number of waves or wave functions. Then we shall discuss wave packet which represents a particle. Shall I continue, or you have a cup of tea? After that we shall continue the next class. Am I audible?
Yes, sir.
Shall I continue, or you have a break, you need a break?
No, sir. Continue.
Okay. So wave packet. A wave packet can be constructed. Oh, बताइए जी, please. Somebody else. विश्व जी बताइए.
Continue class, sir.
ठीक है. A wave packet can be constructed by superposing a large number of waves so chosen that they interfere constructively in a localized region of space and interfere destructively elsewhere. If the localization is constant in time, this can represent a particle. Suppose a wave packet is formed by superposition of a number of waves propagating in x direction. For a simplest case, one-dimensional motion. So we represent this by the wave function psi, which is equal to summation n e to the power I kn minus omega n t. So where n is equal to amplitude of the nth wave, kn is equal to magnitude of the wave vector, omega n is equal to angular frequency. If we choose a continuous possible values of k, we can replace the sum by an integral. So you can write psi is equal to integration minus infinite to infinite a e to the power I kx minus omega t dk. So your ak is the amplitude of psi k corresponding to the momentum p, which can be written as h cross k. And your angular frequency omega is a function of wave vector k. And the value of psi depends on the form of ak. For simplicity, we assume that ak is constant in some interval of width del k around a given value k0 and 0 outside that interval. So you can write ak is equal to 0 in the region k smaller than k0 minus del k, and it is 0 even when k is greater than k0 plus del k, and in between your ak0 is equal to k0 minus in between ak0 is equal to k. So this can be shown in the screen or in figure and figure 2.2. It means that k does not have a precisely determined value. It is distributed uniformly over a band of width 2 del k. This is presented in the picture figure 2.41. And your psi is equal to integration minus infinite to k plus del k 0 multiplied by e to the power I kx minus omega t plus integration k0 minus del k to k0 plus del k a k0 e to the power I kx minus omega t dk plus integration x0 to infinite 0 multiplied by e to the power I kx minus omega t dk. So you can write psi is equal to ak0 integration k0 to minus k to k0 to del k e to the power I kx minus omega t dk. So if you assume that omega is a smooth function of k and expand it in Taylor series, you can have omega k is equal to omega k0 plus k minus k0 d omega by dk when k is equal to k0, so on and so forth. Now neglecting the order of the terms of order k minus k0 to the power n, where n is greater or equal to 2, we get omega k is equal to omega k is nearly equal to omega k0 minus k0 d omega by dk, where k is equal to k0. Or your omega k is nearly equal to omega 0 plus k minus k0 omega 0 dash. So where your omega 0 dash is equal to d omega by dk, where k is equal to k0. Now you substitute this into the original equation I have discussed earlier, and your psi is equal to nothing but a e to the power I k0x minus omega 0 t, and the derivation is shown in the screen. So your a is equal to 2a del k sine eta by eta, where eta is equal to x minus omega 0 dash t multiplied by del k. And this equation represents the Debye wave whose phase is k0x minus omega 0 t and momentum is h cross k. It is a plane wave modulated by a factor sine eta by eta. The amplitude a of psi does not remain constant either in space or in time. Okay, now the group velocity. So a is maximum for maximum value of sine eta by eta, which is equal to 1. So the maximum value of sine eta by eta is equal to 1. So a is maximum when sine eta by eta is equal to 1. And your for that your Vg is equal to omega 0 dash. And Vg can be represented at d by dp, which is called the group velocity of the wave packet. Then group velocity of photons. For photons, m0 is equal to 0, E is equal to Cp. So Vg is equal to d by dp is equal to c. And group velocity of electron in non-relativity case is equal to p square by twice m. If E is equal to p square by twice m, your d by dp is equal to p by m is equal to v, and Vg is equal to v. So the wave packet moves with the velocity of the particle. For relativistic case, if you derive it, differentiate it, then Vg is equal to v. So the wave packet moves with the same velocity as that of the particle. This shows that the group velocity is a meaningful quantity, whereas the phase velocity is not. Since group velocity is associated with a wave packet, a particle has to be represented by a wave packet and not by a single monochromatic wave. And the spatial distribution of wave packet is shown in figure 2.3 as shown in the screen, where your a is equal to, or the amplitude is equal to 2a del k sine x minus omega 0 dash t multiplied by del k whole divided by x minus omega 0 dash t del k, where a is equal to 2a del k sine x multiplied by del k whole divided by x multiplied by del k. And a is maximum when sine x del k by x del k is maximum. So the maximum value of sine x del k whole divided by x del k is 1. This corresponds to x del k is equal to 0. And since del k is not equal to 0, your x is equal to 0. And you can see that the amplitude is not constant. It is like a modulated wave as shown in the screen. The inner wave represents the amplitude, and it is like a modulated wave. Okay. So A vanishes when sine x del k by x del k is equal to 0, or sine x del k is equal to 0. It implies that x is equal to xn is equal to n pi by del k, where n is equal to 1, 2, plus minus 2, plus minus 3, or so on and so forth. And your del x is equal to 2 pi by del k can be considered as the spatial extension of the packet, and your del x multiplied by del k is equal to 2 pi. So the width of the packet in the x space is related to the corresponding width in k space or momentum space by the equation. So del x multiplied by del k is equal to 2 pi. So del x is in configuration state and del k is in momentum space. So this del k and then del x are multiplied, and the result will be 2 pi. So multiplying both sides of the expression, you can have your del x multiplied by del p is equal to h. So localization of a packet in time can be explained like this as shown in the screen, and your Tn is equal to integration nearly equal to del pi by del omega, and T1 is equal to plus minus pi by del omega. That is temporal extension of del t, and your del omega multiplied by del t is nearly equal to 2 pi, or E del E multiplied by del t is nearly equal to h, and this leads to the uncertainty principle of Heisenberg. E t x k or x p, these are the two canonical conjugate variable, and their multiplication looks like this. Then we shall discuss Gaussian wave packet if you have the time. So let us have a break, and we shall meet after some time. Okay, so when we shall meet for the second class? Around 5:30.
Okay, sir.
So thank you. So you have your, please have a break, and we shall meet again at 5:30.
Okay, sir.
Thank you.
Thank you, sir.
In the same
Sir,
link.
5:30.
In the same link, we shall join.
Sir, 5:30 to 6:30.